Okay, so we're on chapter 11, which largely concerns the chemistry of solutions. So the first thing we need to do is talk about some basic vocabulary and calculations. So a solution is made up of a solute and a solvent. The solute is the thing that's being dissolved, and the solvent is the thing that's doing the dissolving. So normally that means that your solute is a solid, and then the solvent is a liquid, typically water. Otherwise, you can think of the solvent as the thing that's present in a higher quantity. So it's obviously possible to dissolve two substances that are in the same phase together. So your solvent is just the thing that you have more of. Okay, so we can talk about solutions as being either dilute or concentrated. Dilute just means that you have a low solute to solvent ratio, and then concentrated means that you have a high solute to solvent ratio. Okay, and there are a few ways that we can show calculations for the concentration of a substance. The one that we'll use primarily is molarity, and you'll notice this uses the capital M as a unit. And that is just the moles of solute divided by the liters of solution. Okay, and then molality is slightly different. We use it less. It's little m, and that is the moles of solute. So we still have the same numerator, and then the denominator this time is kilograms of solvent. Okay, and then the third type of concentration that we can calculate is mass percent. So the mass of the solute divided by the mass of the entire solution equals 100%. So this reminds me to make sure that we're clear, the solute plus the solvent is the solution. Okay, so when we're looking at the mass of the solution, we would want to find the mass of the solute and the solvent separately if necessary and add them together. Okay, and then finally we have mole fraction. So that is the moles of whatever it is we're concerned about. Typically, the sub A here would be the solute, and then you'd be adding together the moles of the solute and the solvent separately to find the mole fraction of the substance. Okay, so if we look at the next page, there's an example of calculating molarity, and you're given grams of your solute, and then you simply convert that to moles and then divide it by the liters of solution that you're given, and that tells you your molarity. Okay, so go ahead and look at the next in-class problem. So it works the same way. Make sure to calculate or convert milliliters here to liters, but otherwise it works the same way. So you'll use the molar mass to convert from grams to moles. Okay, so go ahead and pause the screencast and find the molarity there. Okay, when you do that, your answer should be 1.60 molar. Okay, and so when we say molar, we mean molarity, and we use a capital M as the unit there. Okay, so this next problem, we're actually calculating molarity, mass percent, mole fraction, and molality all with the same information. So go ahead and take a moment to do those calculations. Okay, so when you do that, your molarity should be 0.215, capital M. Okay, and then if we scroll down, the mass percent, okay, should be 0.99% of ethanol. Okay, mole fraction should be 0.00389. Okay, so there's no unit on the mole fraction because your units of moles cancel. Okay, and then finally molality should be 0.217, and we use little m as the unit for molality. Okay. Alright, so there's another problem that you'll have to find all four of these things, and this is good practice because you'll have a quiz that's just over finding these ways of calculating concentration. Okay, so go ahead and pause the screencast and find the answer for the next question. Okay, so your answer for molarity should be 0.427 molar. Okay, and then if you scroll down, okay, your mass percent should be 2.50% NaCl. Okay, and then finally the mole fraction should be 7.82 times 10 to the negative 3, where you could not have it in scientific notation if you didn't want. And then the molality would be 0.438 molal. So molal is molality, and you use little m. Okay, so we can go over those, any of those that we need to in class, but hopefully those are pretty straightforward. Okay, so the next thing that we'll work on is solution stoichiometry. And I'll go ahead and do the first one, and then I'll leave the next one for you to do. Basically, you're just using, given like the molarity and the volume of a substance, you can calculate moles. And so then you can just set up the normal mole fraction and so on for a problem. And we've done some of this in the past. This one's a little bit different because you're combining the concentration stuff with the gases and the stoichiometry all in one problem. Okay, so this reads, blackboard chalk is about 100% calcium carbonate. What volume of carbon dioxide will be evolved at STP if an excess of chalk is reacted? So if this is an excess and this is your limiting reagent, then that's good because they're giving us information about the hydrochloric acid. So we have 0.888 molar of the hydrochloric acid, and I'm going to go ahead and convert the milliliters into liters. This is 0.035 liters of my hydrochloric acid. Okay, so then I want to convert to moles so that I can set up a mole fraction. So if I have 0.888 molar, that's the same thing as moles per liter. Okay, and then I can multiply by my volume to get moles. Okay, so that gives me 0.031 moles of HCl. Okay, and then remember I'm trying to find out about CO2, so I set up a mole ratio. So for every 2 moles of HCl that I have, I produce 1 mole of CO2. Okay. And then the last thing that you have to remember is if you're looking for volume, and the key thing, this is at STP, so you have to remember, and it's also a gas. So for every 1 mole of the gas at STP, that takes up 22.4 liters of space. Okay, so when you do multiplication here, you should find that the volume is 0.35 liters of CO2. Okay, so go ahead and scroll down to the next problem, and this works in a similar way, although you'll have to do a little bit more work to arrive at the correct answer. So go ahead and pause your screencast and find the answer to that problem. Okay, so you're looking for how many milliliters of hydrogen gas are expected, and your answer there should be 466 milliliters of hydrogen gas. Oh, and then this is also a question, the first part. So how many milliliters of hydrochloric acid are needed to react? And so the answer to that part is 168 milliliters of HCl. Okay, so this next part we've discussed along the way as we have previous sections that I've been talking about, but performing dilutions. So as you know, stock solutions are things that are really concentrated, and then we just dilute them with water so that they become less concentrated, because we don't always want a really concentrated solution for doing our experiments. So the way we set that up, this is the derivation for this equation, M1V1 equals M2V2, which is the equation you should use for doing dilutions. And what this essentially is saying is the molarity initial times the volume initial should equal the molarity final times the volume final. And the idea here is that even when we're adding water, the moles of the solute isn't changing. So that's why we can set this up as an equality. Okay, so this is just a picture of a dilution happening. I want to go through one quick example, and I know we've already talked about this a little bit, but what I want to ask is what volume of 16 molar H2SO4 must be used, okay, in order to prepare 1.5 liters of a 0.10 molar H2SO4 solution. Okay, so if you start out with this concentration and you want to end up with this concentration, and this is the volume that you want of that, then how much of this do you need to use? Okay, so you would set up M1V1 equals M2V2. So 16 molar, and we're not sure how much of that concentrated solution that we need, so we leave that V1 as our variable. And then we want to have 0.10 molar solution, and we want 1.5 liters of it. Okay, and so you find that V1 equals 0.009375 liters. That's not very helpful to us. I would prefer that it be converted into milliliters. So you would measure out about 9.4 milliliters of that concentrated solution, and then add water until you get 1.5 liters total, and that would give you the solution that you wanted. Okay? Alright, so one other thing that we need to talk about is what makes things soluble or not. Okay, and there are certain things that we'll consider along the way, but one of the main things that we need to talk about is this rule, like dissolves like. Okay, and what that means is that polar things dissolve easily in one another, and nonpolar things dissolve easily in one another. Okay, in other words, if you have something polar and something polar, those mix. If you have something nonpolar and something nonpolar, those mix. What doesn't mix is something polar and something nonpolar, and we'll talk about why that is. But that's, you know, like the classic oil and vinegar example that people always use, why those two don't mix, and it has to do with their polarities. So vinegar is polar and oil is nonpolar, and so that's why they don't mix. Okay, so in order for something to dissolve, there are three things that we have to think of as taking place, and we're thinking about this on a molecular level. So the first thing that has to happen is that the solute particles have to separate in some way. And so that is going to be, some of this is on the next page, but that is an endothermic process. So we haven't talked about enthalpy yet, but you have to put energy in. So it's a positive enthalpy value. Okay, the next step is that you have to essentially break apart your solvent to make room for those solute particles. So you're overcoming the intermolecular forces in the solvent. So that is also going to be endothermic. Okay, so both of these steps are positive delta H endothermic because it requires energy input. And then this third step, the solute and solvent particles interact. So basically they're forming their own intermolecular forces, so to speak, and so this is actually an exothermic process, okay, because that is favorable for those bonds to be formed. So bonds breaking is endothermic, bonds forming is exothermic, and exothermic is energetically favorable. So these three diagrams here are just laying out sort of what those molecules separating and then coming together looks like. Okay. See if I don't run out of time here. So when we consider all three of these delta H's in unison, the three steps that were described above, that is what is equal to the enthalpy of solution, or the heat of solution. So basically the energy that is required to make something dissolve. Okay? And if this delta H is negative, then that's most likely going to occur because it's energetically favorable. And then if it's a small positive value, then it is likely to occur because of not that much energy input is required. If it's a large positive value, it's probably not going to happen because that's difficult.